Welcome everybody to this webinar about traffic congestion prediction in networks, more specifically in mobile networks. The speaker is me, Hendrikx. I have a background in applied physics, IT, telecom, and data science. I'm the co-founder and co-owner of Hendrikx ITC, Hendrikx IT Consultants, and of the data processing solution OneOptic. Some information before we start. If you have questions, you can ask them. You can do it in the chat during this webinar, and when the answering of the question takes a bit more time, then we can do it in a one-to-one session after the session. So feel free to ask questions if you have them. Thank you for joining. A lot of participants in the webinar, which is always nice to see. You get some interest. This is the agenda for this webinar. At first, we will discuss the question what congestion is in networks, in mobile networks. Then we will talk about framing the problem of traffic congestion prediction, for short TCP. Then we will talk about offline TCP, online TCP. Then we will discuss a case about binary classification for beach covering sites in the Netherlands. And in the end, we will discuss a bit about near real-time TCP traffic congestion prediction. So what is network congestion? The definition, you can get it from Wikipedia or another online encyclopedia, is that in data network and queuing theory, it means that a reduced quality of service that occurs when a network node or link is carrying more data than it can handle. So basically, there are more subscribers than the network resources can process, or a subscriber or some users demand more resources than the network elements can process. And typical effects of network congestions are queuing delay. So basically you have to wait as a customer, as a subscriber. Packet loss, meaning you have bad quality of connection for a service. And another side effect is that you can have blocked connections, so that you are not even able as a subscriber to get access to your service you want. So why should you work on predict congestion in networks? Of course, you want to have happy customers as a network operator, and you want to minimize the unavailability of your network services. Secondly, of course, you want to have a most optimal use of your resources, of your network resources. Basically, you can do the most to get the most out of your network resources, reducing costs. But also, a third reason why to invest in predicting congestion is that you want to grow as a company on the data maturity ladder, if you like. This model you see here, this diagram is called the data maturity diagram. It's from Gartner. It is four levels, and it says something about the maturity of your company or of your organization, how mature you are in the data-driven world. And the first two steps are about that you can explore and get all the data that is available in your organization, so that you are able to do analytics on it, and that you are knowing what is happening in your organization, in your processes, in your systems, and more specific for operators, that you know where congestion is, where capacity issues are in the network, where availability is good, where availability is not good. But the third or fourth steps in the data maturity model are about that you can predict where issues in your network are happening. And the fourth step is about that you can use your predictions and fit them in your processes, so that you can eventually prevent issues like congestion and other issues. So you are going from proactive to predictive. And in the end, in the right bottom, you see the term dark NOC, which is some kind of a hype term these days. The holy grail is that you are able to automate all the processes in your network operations center, so that you don't need any engineers anymore, and everything is automated. I think this is a bit of a Fata Morgana, a bit of a too ideal situation, but this is the ultimate goal of this whole model. So framing the problem, you can look at different angles at the congestion problem, and how you look at it has impact on how to solve it. For example, the definition of congestion, which was shown some slides before this slide, was a bit of a high-level basic definition. But when you have to really work with it, you want to do machine learning AI with this congestion issue, then you have to have a real definition of congestion, of traffic congestion. So then you have to think about, do I want to work with 15 minutes data or monthly data or weekly data? Because this has impact on the way how to solve the congestion issue. But also, if you have a mobile network and you have a lot of counters and a lot of vendors, you have to think about how to define it in which counters to use. For example, you can use counters that are traffic related or resources related, etc., etc. And also you have to think about which QCIs to include, all or some of them. You have to think about what to do with the scenario that one user is using a lot of resources. Is that also congestion, or you say, okay, this is not congestion for us as an operator, etc., etc. But in the end, you get some kind of rule, like in the bottom of the slide, that the resources used in a cell, when they exceed some kind of threshold, the maximum resource that can be used in a cell, P cell max, when that is happening, then you speak of congestion. And also when the average active users in a cell are above some kind of threshold. This is a basic rule for monitoring congestion. So what to predict? You can predict, for example, the timestamp when congestion will occur for a certain area or cell or antenna or site. But also you can predict whether an element will be congested in n hours or days or weeks. That's a different frame, a different question, how to look at congestion. And also you can, for example, put the question other way around and say that, okay, when is an element congested? Not in n hours or days or weeks, but when is it congested in a certain interval? So for example, you could say, I want to predict congestion in 6 hours, and will an element be congested in 6 hours and 4 hours after the 6 hours? So that's an interval. So there are different frames, different ways to look at the issue of congestion. And what I said, how do you ask the question has impact on the way how to work with it. For example, if you want to predict a specific timestamp when a network element is congested, you can do this with time series forecasting. And then you forecast a certain time series, some traffic time series, or network element resources time series. You can do this with linear regression techniques, and then you can forecast a specific timestamp when the congestion will take place. The other two questions are more like a binary classification problem. Binary, since you are predicting yes congestion or no congestion. And then you can use other techniques like the perceptron or random forest, neural net models, etc. So basically you can divide the problem in three areas, if you like. You have the offline context, then you predict congestion in the order of weeks and months on before. So that is the typical capacity management process. If you know that a site or an element will be congested in, let's say, 6 months, then you can take action as an operator and put extra resources on the site so that you can prevent congestion. This process is done basically manually. You get a list of cells, of antennas that will be congested, and then you can make the order to put extra resources in the network. Then you have the online like congestion prediction situation. That is when you want to predict congestions within hours, let's say 6 or 8 hours on beforehand. This is more like an open loop amplified intelligence scenario. This is manually automated, depends on how you implement it. And then you have the near real-time congestion preventing situation. And then you're talking about SON closed loop solutions. The first one, capacity management, is quite traditional. Operators are doing this for years and years. So that's nothing new under the sun. The online traffic congestion prediction scenario is a bit new. It is to do with data science and also exploring network behavior. And the third one, a lot of suppliers are on the market providing all kinds of SON solutions, and these are more or less commercial off the shelf. Just purchase them, deploy them, and you are ready to go. Offline capacity management. Basically, how this is done is you have a time series like this. The time series indicating something like the throughput or the network resource utilizations. This can be on cell level, antenna level, site level. And then you have a threshold with the max capacity. And when the trend passes the threshold, then you have to do something. And this time series can be forecasted. So this way you can predict when congestion will be there. You have several time series forecasting modules out of the box available online. For example, there's a nice module called Profit. It is provided by Facebook, or it's called Meta these days. And with this model, you can do forecasts on time series. This is an example, some Python code fed with some traffic data, and in the end, you can see the last two peaks are predicted time series. So this way you are able to predict congestion in a very simple way. Also, Elastic from the ELK stack, ELK stack, has also built-in time series forecasting features in it. Feed the system with a time series data, for example, traffic or throughput or whatever. And then you can do also some time series forecasting and also predict congestion with it on the longer scale in the order of months, weeks. Then we have the online scenario when you are trying to predict congestion within hours. And this is like this. But first of all, you can't do this. You can't make models for all antennas in the network because it takes too much time. So it is very useful to try to make some categories in your network. For example, you can make some categories. You can find some categories in your network for rural antennas that are covering rural areas, antennas or covering urban areas, highway covering sites, and also, for example, beach covering sites. Because when you do it like this, you have 4 categories. You can train 4 category-specific models, and you can apply them to all the antennas, all the cells of a specific category. And also, the data you can use for the model training depends on the category of the antennas. For example, for rural antennas, you can use a PM, CM, FM data, being the data which is published by the OSS each 15 minutes or 5 minutes. You could use this data for making models, train models for rural antennas. But for example, for urban antennas, maybe also it is very interesting to use road traffic data or event like data, holidays, etc. And the same holds for highway covering sites. But for beach covering sites, it may also be very useful to use, for example, weather forecast data, like in temperature and rain, because the thought is that when rain is forecasted, then there will be less people on the beach, so there will be less chance on congestion. So weather may be an important feature for the model training for beach covering cells. These are
4 categories, but of course you can find more categories. Depends on how you configure your clustering mechanism. But 4 is okay. Then another issue which you have to deal with congestion issues. Congestion is not happening that often in a network, at least it shouldn't. And that means that when you're working with congestion data, that the data set is imbalanced. And imbalanced means that what you can see here, this is a balanced data set, meaning that that the event that you're looking for happens, let's say 60-40, 50-50 in all times. But imbalance meaning that means that the event you are predicting is not happening that much. And for congestions, that may be, let's say 99-1 or even less. So and this is an issue because if you have a model and you can you say, okay, the model predicts that there will be no congestion, then the accuracy of the model will be very high by default, because congestion doesn't happen that often. So you can have suppose the ratio of congestion and non-congestion is 99-1, and you say that the model predicts congestions, no congestions by default, then you have an accuracy of 99% by default, which is very high, but it means not too much. It's not very useful. So you have to look at different measures than accuracy. And the two measures you have to look at with imbalanced data sets are the measures precision and recall. And precision, that is a measure for how many predicted congestion situations were correct. And the recall is how many congestion cases that were predicted correctly. So of all congestion events, how many congestion events were predicted correctly? That is recall. And the other one, precision, is about how many of the predicted congestion situations were correct. And in the ideal situation, you get for both ratios very high percentages. Okay, I'm looking at chat. Okay. How to deal with imbalanced data sets? Some strategies. There are two basic strategies. You can do one thing, that is making less samples in the abundant data sets by filtering it out. So then you have a better ratio of congestion and non-congestion. If you filter out the non-congestion data sets, then you get a better ratio, of course. And you can also do it the other way around. That is by oversampling, and that is making more samples, generating more samples of the rare data set. So, and that can be done with techniques like repetition, bootstrapping, and SMOTE. You can look it up. The URL is in the slide deck. By the way, we will share the slide deck after this webinar, so you can look it up yourself. Oh, I see a question. Yes, the model should be optimized for that depends, but I will venture in this after the webinar. I was looking at the chat. So I go further. Then a case. We did a project some time ago. It was a binary classification problem. So we tried to predict whether a network element was congested, yes or no, binary. It was about 4G beach covering sites in the Netherlands. So we did, of course, data exploration. These were the beach covering sites in the Netherlands we were investigating. As you can see, the two colors. This was a multi-vendor network with two radio vendors, Huawei and Ericsson. The data sets we used the PM, CM, and FM data directly from the OSS, from the both OSSs. And we got some KNMI data, being weather data. And we used some weather forecast data. We got these from the platform Open Weather. Then the counter data.
temperature, of course, and weather forecast like rain, clouds, and also temperature. So the K and MI data was the actual temperature at a certain timestamp, and the open weather data was weather forecast data. Like I said, we already had the PM, CM, and FM data because we have a solution called Monoptic processing this data. So it was available to us. All the data we needed was available in a relational database. So it was clean, complete, and processed and prepped. That was very good to have the data already. Dashboards, etc. Yeah, per vendor. The problem, the framing of this specific case was like this. We had five framings. The first one was to use only PM data and no weather forecast data and no KNMI data, only PM data. And then we had data for six hours. We had some network resources data. We had some traffic data, some other parameters, and based on these parameters, 14 features, you call them features, were used to train the model. With another framing that we used 15 features. We also had the same set as the previous one, but then also we used the temperature, 24 hours forecasted ahead. Another scenario with also rain and cloud forecasted data. And we had some other frames with temperature with 12 hours forecast and also another 12-hour forecast scenario. And so we had 5 scenarios to work on, and then we could decide which one was the most precise and gave the best results. And the question we investigated was based on this data, on these 6 hours of data, T0, would a cell or a sector be congested in 6 hours in this interval, 8 hours after 6 hours. So it is a binary yes, no classification problem. More technically, what did we use? What did we do? We had this feature data, which also mentioned in the previous slides. 3 models were trained, a perceptron model, a random forest model, and a neural network binary classifier. Like I said in the previous slides, these kind of models and are free available on the internet. So these days you are able to do it yourself. And after that, we got some scores. You can see here the precision and recall score is being a ratio, and also some other scores, which are also data imbalance specific scores. Because accuracy, just the plain accuracy, is not useful in imbalanced data sets problems. Okay. This is a short overview of how you can display results of a binary classification problem. This is a nice matrix with 4 quadrants, and these are the true negatives. These are the true positives in the diagonal, and these are the false negatives and the false positives. So in the ideal situation, all these is 0, this is 0, this is positive and positive, because then you have an ultimate ideal trained model. And the horizontal quadrants, these two, the ratio between these two numbers is the recall, and the ratio between these two numbers is the precision. And this way of displaying results is very intuitive. What we found in this specific project was there was a trade-off between precision and recall, because like I said a few moments before this, in the ultimate situation, you are going for the 100% precision and 100% recall. In this specific project for beach covering sites, we found a trade-off. We got a situation that with a certain frame, a certain set of features, a certain set of parameter settings, we found a precision of 53%. And a recall of 9.4%, which is quite low. On the other hand, when we got a high recall, we find quite low precision. And again, you can deduce the recall from this square by the recall, the ratio between these two numbers. So a lot of true positives were there, 800, about 800, but also 211 predictions were incorrect. And here the other way around, this was 50-50, precision is 53%, so that's the ratio between these two numbers. But then the recall was quite low because there were a lot of false positives. Yeah, false positives. Another way to display results. This is a matrix of all the combinations you can get from the frames I was mentioning 2-3 slides ago, like in the 15 features, the 17 features, the including the forecast data, the 12-hour forecast data, the 24 forecast data, yes or no. Then you get a matrix of all possible model trainings. Also, these are the models we used, the neural net, the perceptron, the RF for random forest. And then we had also some variation. We experimented a bit with the how to combine the data because it was multi-vendor data. So we did model training for the vendors separately, like in Ericsson and Huawei. But also we did a combined model training, and we did the model training on cell level, also on sector level. And this resulted in this matrix. And then we find that the best recall results were for the Ericsson on sector level, for the neural net, and also the perceptron being 98%. So this means that for Ericsson on sector level, with the neural net and also the perceptron, we were able to predict 98 of all congestion cases for Ericsson. And for Huawei, it was about 79, 80%, 88% even. So this is what data science is in the real world. You work with the data, you explore the data. Based on the results you have, you build on further to new results, etc. Okay, then we go. Okay, and this is and the results of the predicted results you have, and this when will the site of a cell be congested. The output, if you know that some hours on before, can be fed to a process, and then an engineer can remotely adjust the network based on the findings, and he or she can remotely change the tilt of antennas, being electrically, or the power can be adjusted, or even the azimuth can be adjusted remotely. There are suppliers providing azimuth adjusting solutions remotely. You can also tweak the MIMO configuration, etc., etc. And this is called an intelligence amplification scenario, or an open loop. An open meaning that the predicted results are not coupled directly into the organization, into the system adjusting the network, but there is a human being determining whether the suggested adjustments should be done, yes or no. Open loop. If you're going for the closed loop, for the SON solutions, in real time, then you have several vendors providing all kinds of AI platforms, like Huawei, Nokia, also Fastmetrics. I found that one a few weeks ago. It's a nice vendor providing azimuth SON, also interesting. That is testing, etc., etc. So that is this is for the self-organizing SON solutions. This was the webinar. Nicely done, 30 minutes. Don't hesitate to contact us in case of any questions, or if you want to do some machine learning AI with us, or you want to know more about it, you want to share your data, we can work on it. Or if you want to know about OneOptic, the data processing platform, that's also an option. Please contact us. Yes, I see a question in the chat box. Remote azimuth. Yeah, apparently there's a supplier providing remote azimuth adjustment solution. So you are able, like in the electrical tilt, to adjust the azimuth remotely.
I had an earlier question from Vijay Sambe, if I
Yeah.
pronounced that correctly. He asked if you could get the specs of the data set where this experiment was run with the congestion prediction.
Specs like how many data and which period, etc., etc. Is that what you mean, Vijay?
I assume.
Yeah,
I think
it was a case of 40 sites, not that many. The data, the PM data, was over an interval of 7 weeks. So we had 7 weeks of data, but it was in hardware. Hardware. Okay. It was done with Python scripting on a typical desktop. So yeah, no big cloud configurations or heavy servers. No, it was done with Python scripting on a desktop. If you want to know more about it, just contact me and then I can elaborate on it. I see also a question from Wouter de Leeuw about how the beat sites were selected, labeled. This was done by the operator. So the operator said these are beat sites, and it was like, yeah, Python is also friends. Yeah, I know, Hans. Yeah, so that was how it was done. The operator specified the beat site label. More questions? Or do we have a shock and awe situation? Everybody is awed. Feel free to ask more questions. Now I see a small. Okay, R is also a nice environment to work in, which we work on machine learning AI projects. Yeah, I have no specific preference between Python and R. You can use both. What do you use for maximum possible PRB utilization? Is a question of Rob Mulder. This has been done together with the operator. Like I said, it has to do with framing the problem. So the operator has specified this is what we see as congestion. So that was how it was defined, more or less. But I can look that up if you want to have more information, Rob Mulder. Then send me an email and I will give you the spec of the maximum possible PRB utilization. No problem. Another question, Alexei. How did you compensate for COVID traffic congestion variations? Yeah, that's a very good question. We didn't actually. So we did have the data for seven weeks. That was the data we had to work with. And yes, it should be very good to do the model training again in the post-COVID situation. But we have to wait a few months, I guess. Maybe this summer. But it's a good question. Did you test your models with site cells in different areas which weren't exposed to training learning phase? Not yet. The case I mentioned in this slide deck was beach covering only. But yes, you should also do this for, let's say, highway covering sites or urban sites. Yeah, would be very interesting. Yeah. And again, if you have questions and you want some answers, just drop me an email. No problem. More questions? then I think we can complete this webinar, or are there still? Yeah, exactly. Just have a big mailbox. So send me an email and I will answer them swiftly.